So the lab that we are going to be doing tomorrow, you are going to be mixing an acid and a base together, and in the process of mixing an acid and base together, your goal is to get to a neutralization. So the generic neutralization reaction is acid plus base will make water and a salt. And so what ends up happening is that because water is clear, it's hard for us to know when water is formed. And because the salt is going to be aqueous, it's also hard for us to know when we've gotten to exact neutralization. So one of the ways that we combat that is, or we figure it out rather, is we use what's called an acid-base indicator. And an acid-base indicator is a compound that is usually formed from a weak acid or a weak base, but the compound itself is color sensitive to pH. That is, when the pH changes just enough, it will change color, or it will shift from one color to another color depending on what you're doing. Now, the acid-base indicator that we are going to use tomorrow is an acid-base indicator that's on this list. It's the fourth one from the top, called phenolphthalein. When you put the phenolphthalein, which is a weak acid, into an acid, it stays colorless or clear. When you add enough base that you have now used up all of the acid, and you're making water, and eventually you make it a little bit basic, it turns pink. And when it turns pink, that means that you have gone just past the neutralization point, or the equivalence point, which we're going to talk about now in a minute. But basically, the color of the compound will change as the solution changes from acidic to basic. Now, this generic equation on the bottom is not something that you need to memorize, but you do need to understand that HIN is the weak acid of the indicator, and as we add more base to this indicator, eventually we make H3O plus, and we make a lot of indicator minus, or IN minus. And when that IN minus gets to a certain threshold, the color will change. So like in the case of methyl orange on top, it will become orange when it's in a weak acid, and when there's enough conjugate base made, it turns yellow. And and then at that point, you know that you're somewhere at a pH range of 4 to 6. But like if you have a hot tub or if you have a pool at home, at some point you probably have had to do some type of testing of pH values. And if you do that, depending on the kit that you have, you take a sample of the water, you drop a little special magic solution in there, and you shake it. And if it changes a certain color, then it's bad, and you have to shock the pool. But if it stays within the appropriate color range, then you're fine, and you can just go on with your day. And that's basically an acid-base titration in the small scale in the real world. Now, in titration, which is what you're going to be doing in lab tomorrow, we always use an indicator, and we've already said that an indicator is a weak base or a weak acid. But the definition of titration is the controlled addition and measurement of a solution of a known concentration required to completely react with the measured amount of a solution of an unknown concentration. Because it's a neutralization reaction, we make water, which is really hard for us to visually see, so we use the indicator. You will always know 2 volumes and 1 concentration in the lab tomorrow, and in the practice problems today. And excuse me, sorry. And you'll be able to always calculate the unknown concentration, or sometimes you'll know the concentration, the 2 concentrations in 1 volume, and you can calculate the volume necessary to titrate something. So the big thing that I would like you to take away from here at this particular point is that we know when to stop titrating when you've reached what's called the equivalence point, also known as the end point. This is the point in which moles of acid are equal to moles of base in the Erlenmeyer flask underneath the burette in your titration. And I'd like to try to explain why in a second using some math. So if I calculate, or if I say that I have the molarity of my acid, which is equal to moles over liters, and I compare it to the molarity of my base, which is moles over liters. If I solve for moles, right, I would take liters times moles of acid, which equals moles of acid, and I can compare that to molarity of base times liters. So what I'm making a comparison here is that when we are at the equivalence point or the end point, the titration process is over and the moles of acid are equal to moles of base. And we can use that to help us calculate that all the way through. So when the moles of acid equals the moles of base, the pH of a solution should be around a pH of 7. And in our titration tomorrow, that's when the indicator will tend to change colors. So if we're working with a strong acid, if we were working with a strong acid and a strong base, okay, we can use the titration formula above as long as the mole ratio for the neutralization reaction is 1:1 for moles of acid, or for moles of acid to moles of base. If it's not 1:1, you have to calculate it differently, and I'll show you how to do both types of calculations today. So, any questions about this slide here? Yeesh. Okay. In example number 8, we are asked to calculate the molarity of the base used in this particular titration reaction, in which case we neutralize the acid with the base of an unknown concentration. So the first thing I'm going to do is I'm going to write my neutralization reaction, which is HCl plus NaOH reacts to form water and sodium chloride. In this case, the sodium chloride is going to be aqueous, the water will be considered liquid, the original solution of the sodium hydroxide will be aqueous, and the acid will also be aqueous to begin with. So that's our equation, and if we were to balance it, in this case it happens to be 1:1 to 1:1. So we could use the titration formula above, but I'm going to show you how to do it the other way first, and then I'll work it through to use the titration formula. So the other way says that in this case, because I know the volume and the molarity of my acid, I can calculate moles of acid. So I'm going to take molarity of acid is equal to moles over liters. And so in this case, I'm going to take the 0.098 molar HCl will equal moles of HCl over, and this is in milliliters, so we have to change it to liters, so 0.0347 liters. So I'm going to take the 0.098 times 0.0347, and I'm going to get a value for my moles to be 0.00 sig figs says 34 moles of acid. So at this point, I'm going to use stoichiometry to calculate the moles of base at the neutralization point. So I'm going to take the 0.0034 moles of hydrochloric acid, and I'm going to note that the mole ratio is 1 to 1 up here, so I'm going to have 1 mole of hydrochloric acid for 1 mole of sodium hydroxide, and hopefully we will be able to easily see that the number of moles of sodium hydroxide present here is 0.0034 moles of NaOH. So now that I know the moles of acid and the moles of sodium hydroxide, I can then go ahead and in order to find the molarity of my base, I'm going to take molarity of base is equal to moles over liters. So in this case, I know that I have 0.0034 moles of NaOH divided by, now this is the volume of the base that we used, so I'm going to change that to liters. And when I calculate that out, I get a value for the molarity of the base to be equal to 0.34 molar. So this is, I guess, for lack of a better term, the long way. But again, this we can do this for any neutralization reaction. So this process we can use for any neutralization reaction. Okay, but yes.
Why did you use that NaOH for the molarity of the base? Then why did you put on top? Yeah.
Say that again.
Why did you, for the molarity of the base, why did you put the number of moles of NaOH on top?
Because the formula for molarity of the base is moles divided by liters. And we took moles, we calculated moles of acid, and we converted moles of acid to moles of base, right? That, so my 0.0034 moles of HCl, I had to convert to moles of base, right? So so in this case, they were the same. And so at that particular point, I then took moles divided by liters to calculate the molarity of the base, because moles is different than molarity.
So you pretty much just use the first half of the equation, you don't worry about the second at all. Like you're just using the first half, you're not using anything on the second half. I don't know.
The first half of the chemical equation?
Okay, yeah.
Is that what you're asking?
Yeah.
Yes.
Okay.
Yes. That is what you're using. All right. Now, in order to show you the other way to use this, the titration formula says molarity of acid times volume of acid will equal molarity of base times volume of base. So in the given problem, we knew the molarity of the acid to be 0.098 molar HCl, and we knew that we had the volume of the acid to be 0.0347 liters. We're asked to calculate the molarity of the base when we used 10 milliliters, so that would be 0.0100 liters of the base. So when I solve for base, molarity of my base in this case, 0.098 times 0.0347 divided by 0.01, I get a value this time of 0.03, or not 0.34 molar NaOH. So this works really well when the ratio is 1 to 1. So when the moles of acid in the balanced chemical equation and the moles of base in the balanced chemical equation is 1 to 1. So we can really only use this So we can only use that formula when the ratio of acid to base is 1 to 1 in the balanced chemical equation. So if the ratio is not balanced, if the ratio is not 1 to 1, you have to go through the process above. If the ratio is 1 to 1, you can use moles of acid times volume of acid equals moles of base times volume of base. Any questions about that?